Today we're going to finish section 1.3, and we're going to change gears just a little bit, and we're going to talk about truth tables. Truth tables are used to show all of the true or false possibilities for statements. So I'm going to talk to you first about negation. So if we talk about P being the statement, that's just a letter used to represent what the statement is, then if we're talking about the negation, we put a tilde in front of it and talk about it being the opposite. And we saw that tilde used last time. It's the opposite of the statement. It's just the notation for that. It's kind of like what we use when we use a negative sign. The opposite of 5 is -5. So we use the tilde for that for statements. Now in terms of truth tables, a truth table looks something like this. We put the column header as a statement. So we're going to say compound the statement P. And the other statement we're going to put as tilde P, or the negation of P. So if the statement P is true, then its negation would be false. And if the statement P is false, then its negation would be true. So you're going to see a bunch of T's and F's when we're working with truth tables. Now there are several different types of statements. One of the statements is called a negation. So you take the statement and you reverse the language to be the logically opposite statement, right? That's the one we did last time. There's also something called compound statements. So compound statements is when we join two statements together. Kind of like when you learn about compound sentences, right? So this is very much the same thing. A compound sentence is going to be joined by one of three basic variations of words. The words and, or if then. And the same is true for compound statements. Statement's just a sentence that's actually stops, right? It's not a question or a command. So two statements that are joined with, we call it a connective, such as the words and, or if then. Now the first one we're going to talk about is what's called a conjunction. A conjunction is a statement joined with the word and. So something like, I teach math and I am a mom. Those are two statements. I teach math, I'm a mom, and they're joined by the word and. That's all the compound statement that is a conjunction is. Now the symbol for that, if P and Q are those two statements, that is P is the statement I teach math and Q is the statement I'm a mom, then the way that we use, the symbol that we use to show that they are joined by a and is this upside down V. Okay? So this is read P and Q. That's how we think about that. That upside down V is the is and. And when we're working with a truth table for this, I'm going to make a column header that says P, a column header that says Q, and then I'm going to show you how we create the column that says P and Q. Now, one possibility when we're dealing with truth tables is we could have two statements that are both true, right? I am the classic example that I just said, right? I gave you two statements about me that are both true. I teach math and I'm a mom. They're both true about me. Now we're going to fill in this last column in a minute, okay? Second one, maybe the first statement is true, you teach math. The second statement's false. That is, somebody's not a mom. Dr. Marsh, she teaches math. Some of you have had her. She's not a mother, okay? Third possibility, maybe you don't teach math, but you are a mom. Okay? So that would be, give me one of your professors. It's not a mom. Or that is a mom that doesn't teach math.
Dr. Ezell.
Dr. Ezell. Okay? Professor Ezell, right? Because Dr. Ezell actually is not a mom.
Yeah.
Yeah, he's a dad.
Yeah.
That's okay.
Sorry.
Yes, Professor Ezell, his wife, yes, would be a good example. She doesn't teach math, but she is a mom. Okay? Last one, maybe you have an example of someone who doesn't teach math and is also not a mom, and then we can use Dr. Ezell. So we'll use both of them today. All right, so that would be a statement that's false about both of them. Both of those individual statements are false. All right, so what we're going to do is we're going to fill in this last column now based on that information. So thinking of those particular professors that we just mentioned. So I'm the first example. So if I come into the classroom and I say, I teach math and I'm a mom, that statement about me would be a true statement because both of the individual statements are true. Dr. Marsh walks in. Dr. Marsh says, I teach math and I am a mom. That's false, because she's not a mom. So it's a false statement if she came in and said this to you. Professor Azell comes in and says, I teach math and I'm a mom. False. She doesn't teach math. What does she teach? English? Okay. So this is a false statement if she comes in and says this. Last one. Dr. Azell comes in and he says, which sounds funny at that point, right? He says, I teach math and I'm a mom. And you say, man, that's false on so many levels, right? No. So it's definitely a false statement. All right, so the only way that a compound statement is true is if both of the individual statements are true. That's what this is showing us, okay? So if you have both individual statements true, then the compound statement is true as well. Otherwise, the compound statement is false. All right, let's use the next one. The next one's called a disjunction. So a disjunction is a statement where it has the or in between. And the difference notationally is instead of it looking like the upside down V, it actually looks like a V. And we understand this to be the phrase or the word or between them. All right, so we're going to set up that same truth table with P, Q, but now it's going to say P or Q. And we're going to think of this just like we did before with the same four professors because we already got started down that road, so we're going to continue. It's still possible both statements are true. It's possible the first one's true, the second one's false. It's possible the first one's false, the second one's true. It's possible they're both false. Now, this part of your truth table, if you have two statements, P and Q, is always going to look like this. Underneath the P column, it's going to say TTFF. And underneath the Q column, it's going to say TFTF. It's always going to be in that order. So if you're checking the back of the book, they're going to assume that you've put it in that order. So just for consistency's sake, go ahead and go with that. I mean, if you change up the order, it doesn't make it wrong. It just means that it's going to be difficult for whoever's grading to make sure that you got the right place on everything else after that. Okay? So now we've got the word or. So if I come in and I say, I teach math or I am a mom, that's actually a true statement. It sounds funny to say the or there because both of them are true, but logically it's still true. I mean, one or the other's true, they're both true, so it's true. Dr. Marsh walks in and she says, I teach math or I'm a mom. Also true, because she teaches math. Professor Azell walks in and says, I teach math or I'm a mom. It's true, because she's a mom. Dr. Azell walks in and says, I teach math or I'm a mom. False, because he is neither one, right? So on a disjunction, most of the time the result's true. If either of the individual statements in the truth table are true, then the result's going to be true for an or statement. But if both of the initial conditions, both of the initial compound individual statements in the compound statement are false, then you get a false result. Okay, is everybody good so far? Okay, I want to go to the very end of the slideshow and present you with one more that's not listed in here, but you have like one or two questions about it. Because there's one other type of connective that I mentioned that I didn't do a table for yet. Do you remember what it was? Somebody said it. No, I thought I heard it. If then, right. The thing that says if whatever, then. Okay? So first of all, the notation for that looks like this. It's got an arrow. So P, arrow Q means if P happens, then Q has to follow. I wrote this down anywhere. Okay, we'll talk more about the conditional statements in terms of the language in a moment. But this notation actually has a truth table that looks a little different, and it feels a little awkward. So I'm going to show you how this works so that if you encounter this, you'll know what to do. Now, like I said before, the P and the Q columns never change. We're going to use the phrase for P, I am a mom, and for Q, I am a woman. Okay? So let's think about how this works. If someone walks in and it's me, and I say, I'm a mom, And in fact, I wouldn't even have to walk in. I'm standing out in the hallway, and you know the person standing out in the hallway is a mom, then you automatically know that they're a woman, right? It's like a requirement. By definition, that has to work. So if that happens, the true statement would follow. This would be a true statement. If I'm a mom, then I'm a woman. Yep, that's true. I can check that off, no problem. The opposite doesn't work at all, right? You can't say I'm a mom and then I'm not a woman. That's not going to work, okay? So it can't be true that the first statement's true and the second one's false. That does not work with this example. So if I have the first statement true and the second statement false, that is a false conclusion. It would be false. The other two are the ones that are tricky. You see, if the person out in the hallway says, I'm not a mom, then you have no idea if they're a woman or not, right? There's no logical way that you can say for sure that they're a woman or a man. So, by default, these become a true statement. The idea is that you're giving them the benefit of the doubt. If they say, I am not a mom, but I'm a woman, you could say, yep, that could be true. I'm not a mom, but I'm a man, yep, that could be true. Both of those statements could be true. Okay? It's like giving them the benefit of the doubt. You can't say for sure that they're lying, so you have to assume they're telling the truth. Right? Innocent till proven guilty. You guys know what I'm talking about, right? It's the same idea with truth tables. Okay? So if you can't prove that that statement would then result in a false statement, we say that the statement is true. Okay, we'll come back to that in a little bit. Okay, where was I? Here we go. We're going to create a couple of truth tables. These first two truth tables don't have that arrow in them yet anyway. They've got those connectives with the or on the second one and the and on the first one. All right, so when we create a truth table, if we have P and Q in the notation, we're going to have a column for P and a column for Q. So I'm going to have a column for P, a column for Q. So you can always start a truth table. If you get flustered and can't remember how to finish it, okay, but there's no excuse for not being able to start it because they always start the same way. I'm going to have a column for P, a column for Q. The column for P has 2 T's, 2 F's. The column for Q alternates. Now, the last column, where we would have had a last column before, isn't quite enough here because in our original statement up here at the top, we're not combining P and Q. We're combining P and not Q, the negation of Q. So we actually are going to create a column now that's for tilde Q, or not Q. And then we can write the column header that combines P with tilde Q. All right, so it's very easy to get the tilde Q column as well. What do you have to do? Yeah, you just take the Q column and you do the opposite. So since the Q column went TF, TF, the tilde Q column is going to go FT, FT. Now what we're going to do is we're going to take this column with P and this column with tilde Q, and we're going to combine them with the idea of an AND statement. When is an AND statement true? When both statements are true. So on the first row, I have a true statement and a false statement, which gives me false. On the second row, I have a true statement and a true statement, which gives me true. The third one and the fourth one both start out false, so they are both automatically false because they don't have two T's or two trues in them. And then you're done. Okay? That's how you create a truth table. Now, the next one as the example is actually easier to do. And the reason it's easier is because it gives you more information. Take a look. It tells you P is false and Q is true. What that means is that you don't have to create a whole truth table. You only need one line of it. You need the line where P is false and Q is true. So the information that you set up along the column headers looks the same. It's just you're only going to have one line. So you're going to have a P and a Q because they're always going to have those. If P and Q are involved, P and Q get their own column header. But you're also going to need what? Not P. What else? Not Q. And then what? Yeah, the combining of all of it. Not P or not Q. And again, the reason I don't need lots of columns in this rows in this truth table is because I'm told P is false, Q is true. So I know which line of the truth table I'm on. There's no reason to do anything else of the table because I already know the information about P and Q. So we're going to fill in the rest of those details. This says tilde P. What's tilde P then? True. How about tilde Q? False. And then I'm supposed to compare tilde P and tilde Q with an or statement. So when is an or statement true? When either one of them are true. And this one is true because I've got one of them true. Now this is the work, if you will, that supports what we're actually asked to find. We're asked to find the truth value. The truth value is the final outcome from the table. And T means true. So the answer is true. The truth value for this compound statement is true. All right, let's take a look at some logical equivalencies. We call something logically equivalent if when we create their truth column, they're identically the same. Okay? So if we had the same truth value in every possible situation for two outcomes, we would actually see that those outcomes are the same logical outcome. We write that like an equal sign, but it's got 3 lines instead of 2. Can you guys see that clear enough? It's got 3 lines between it. So if the two statements were logically equivalent, it looks like this. De Morgan's laws tell us a really nice logically equivalent set of statements. They tell us that if I have P and Q and I do the negation of it, I get the negation of P and I get the negation of Q, but what happens in between? It changes, right? It started out as an and statement, it becomes an or statement. Okay? And the same thing is true if I start out with an or statement. I still negate each of the individual pieces, but then the and statement or the or statement becomes an and statement. Okay, so we're going to do 2 examples of this. The first example, example number 4 that we're going to do is just notation on how that works. All right, so this one says I've got negation. This is to find the negation of P and tilde Q. So the first one started out P, which means it becomes what? Not P, exactly. I need to put the tilde associated with the P. It started out as an and statement, which means now it's an or statement. And it started out as not Q or tilde Q, which means it becomes Q. So notationally applying this principle is just applying it to each individual piece. 3 things change. The 2 symbols change and the connective in between changes. Now let's say again?
Like instead of the equal sign, the examples are supposed to be 3 lines?
You could, yeah.
Does that matter?
Yeah, it won't make any difference, but yes, you're right. They're logically equivalent, so it would be good to use the triple equal sign. Yeah, you're right. All right, let's do an example. Oh, I'm sorry. I'm going to verify first one for us. Okay. Example number 5 says that we're going to verify that the tilde P and tilde Q that we just started with before and our answer to example 4 are actually logically equivalent. So we're going to actually show that it really worked. We didn't just make it up and say, hey, look, this cool feature, and it didn't work. So we're going to create a truth table for each of them. So the first one's going to have P and Q in it. In the first truth table, I need the left-hand side, the original piece that I started with, right here. So I need P, which I've got, but I also need tilde Q, which I don't have. So I'm going to get a column for tilde Q next. The next thing that I need is I need to join the P and the tilde Q with an and statement. It's what's happening inside parentheses. Just like when you're working with numbers, we work inside parentheses to the outside. So I need a P, whoops. And tilde Q. The last piece of information that I need is I need the negation of that. The negation of P and tilde Q. Is everybody good with that so far? Yes, maybe? Okay. So just like with the others, we start out 2 trues and 2 falses, and then we alternate. Tilde Q, what's tilde Q going to be?
False, true, false, false.
The opposite of Q, so false, true, false, true. Now to do P and tilde Q, whoops, P, tilde Q, I compare these two. It's supposed to be an and statement. When is an and statement true? When they're both true. Well, the first line says true and false, so that's false. The second line says true and true, so that's true. The third line says false and false. False, right? 2 falses is false. And the last one says false and true, which is also false. The only way an and statement is true is if they're both true. It would only happen on row 2. Now, the last column says I'm going to negate the column that I just created, right? So if I negate the column that says false, true, false, false, what do I get? True, false, true, true. All right, so this was the first truth table that I created. Next truth table over here. What I'm going to do is I'm going to create the truth table, but I'm going to use the result I got over here, which was tilde P or Q. So again, I've got a P and a Q in the information, so I need a column for P and a column for Q. According to what I figured out, though, I also need a column for what? Tilde P, right? And then I just need to put them all together with the or statement between. Right? I've got the tilde P, I've got the Q. So now I'm going to do, this is what I'm working on right here. Whoops. Now I'm going to do the tilde P or Q.
Okay, I'm confused on why you had to have the 2 on the end of the first one.
The 2 on the end
Like
of
in
the
the
first.
first table,
Yep.
the second or the last 2, like why'd you have to have the...
Why
both
this
of
and
them?
this? Is that what you mean?
Yeah.
Okay, so the first one that I've got the green arrow pointing to is the stuff that happened inside the parentheses.
Okay.
So just like with algebra, we work inside a parenthesis first. And the last column is the fact that there's something else going on outside of the parentheses,
So,
which
like,
was the
that's
negation.
That's like the answer we got. and
Yes.
then we're using it to verify the equation that we got now.
Yes,
Okay.
we're going to compare the final column of this truth table that we just created, that very, very last one,
Yeah.
with the final column of the one we're creating now.
Okay.
And if we did it right, we should get the same TF combination that we did.
Okay, I got it.
Right. All right, so let's take a look at this one. They start out the same, right? True, true, false, false, true, false, true, false. That's always going to be the same. Tilde P, though. What's tilde P going to be? Right. I'm going to go back to column for P, which is true, true, false, false. I'm going to get false, false, true, true. And then I'm supposed to compare tilde P with Q to create an or statement. When is an or statement true? When either of them or both are true, right? So in the first row, the ones that are highlighted in blue, I have TF.
True.
That's true. The second one, I have FF. That is false. The third one, I have TT. And the last one, I have FT. And look at that. I feel like I should change my color, so give me that just a second. These match, don't they? TF, TT, both of them. That's what makes them logically equivalent. Their column that corresponds to them in the truth table is identical to the other one. All right, so let me do one with some words so that you can say, okay, yeah, and now from a practical sense in terms of language, I get it too. So here's an example. It says, it is not sunny, and I will go for a walk. That would have been yesterday at the beginning of the day when it was nice and cool and rainy outside, right? I don't know about you, but that was actually very nice. It is not sunny, and I will go for a walk. Well, there's two statements here. One statement says, it is not sunny. The other statement says, I will go for a walk. And what happens between them is the word and. Now, that's three things that all have to change in order to change this to its negation. It says, it is not sunny. What's the negation of that? It is sunny. Okay, now I've got the box where it says and. What do I do for and? I change it to or. Then I've got the statement that says, I will go for a walk. It's I will not go for a walk. That is the logical opposite of the first statement. In order for the first statement to be false, it is not sunny and I will go for a walk, one of those statements that it was originally said with the and between them has to be wrong. Either it was sunny, like today, or you just didn't go for the walk. You woke up too late. Okay? Now, it could be that both of the statements changed. That's possible. But you needn't have both of them changed to make the original statement false. You need to just have one of those pieces different. All right. Let's talk a little bit about those conditionals that I mentioned before. That arrow statement, that if-then. That if-then kind of statement is called a conditional statement. If P, then Q. And I already mentioned this notation, the P and the arrow, the Q. The if part of the statement, that is the P, the way that we're writing that, is called the hypothesis. If I get done in time, if it's not too hot, if whatever. The resulting part, the then part, is called the conclusion. If I get done in time, then I will go to the rock. If it's not too hot, then I will go for a run. Okay? It's the then part is called the conclusion of the conditional. And so we're going to do a couple of language exercises with this kind of a statement. It says, example 8, let P be the statement God loves, I'm sorry, I'm the wrong one. Let P be the statement you build it, and Q be the statement they will come. So this is way before your time, but do you know what this comes from? I saw a couple people nod. Do you know what it's called? Field of Dreams. This is from a movie called Field of Dreams. If you build it, all right, they will come. All right, so the first statement is giving you language. And what we're asked to do is to change the language into symbols. Make sense? So our symbols are going to have some P's, some Q's. They may have some ands or ors or arrows. They may even have some negations in them. The first one says, they will build it if you come. So the if you come part is actually where the statement starts. It sounds like it's happening later on. It sounds like what they're doing is they're talking about the conclusion first. And in reality, they sort of are, but this is the if part. It's really the premise or the hypothesis of my statement. If you build it, they will come. We use the if-then this way sometimes as well. I'll go for a walk today if I can find somebody to walk with me. We write it like that. We think of it that way sometimes too. But the if part's really what we have to do first. That means we're going to try and find the person to walk with us, and then we'll see what happens next. All right, so if you build it, what symbol does that represent? P. Because this is an if-then statement, what comes next? An arrow. And the conclusion of that is they will come, which is the Q. So this is P, arrow, Q, but written in a way that's a little bit different in terms of the language, in a way we use all the time. This now says, it has the if at the beginning, it says, if you do not build it. What's that telling you to do? That's negation of P. But it's still an if-then, so I put an arrow. It says, then they will come. That's Q. So this is just another statement. I'm not saying that it's the same statement as the earlier part A one. It's just another statement and how the symbols would look with it. Okay, you guys with me so far? Okay, we're going to do the next one exactly the opposite. These are the statements. P is the statement, God loves me. And Q is the statement, I am a sinner. They're statements that are both true, right? I hope you believe that. They are. All right, so the first one actually gives us symbols P, and I have this upside down V, and then I've got the Q. So what does P stand for? God loves me. So we're going to write that down. God loves me. What am I going to write next? And. Because this upside down V symbol is the and symbol. And then what's Q? I'm a sinner. Okay, the next one's got an arrow with it, right? What is that telling me?
If then.
It's an if then. So I'm going to start with the word if. That's the easiest way to write this. If what? If I am not a sinner, then what? Then, because I've got the then arrow, right? Then God loves me. And unfortunately, there are a lot of people who believe that, aren't there? But the only way that's going to work is if I get somehow good enough. All right, let's take a look at one more. All right, this is a contrapositive. If you have the statement P arrow Q, if P then Q, the contrapositive statement is the statement where you reverse the order of the P and the Q and you negate them both. You have to do both things. So instead of it having P arrow Q, now I have negation of Q, arrow negation of P. So I've both changed the order of the P and the Q, and I've made the negation of each one. Now, if you do that, you create something called the contrapositive. And the contrapositive and the original statement are logically equivalent. And we could create one of those logically equivalent tables, just like we did earlier. We do a truth table for them when we find out that in the end they both have the same column with the same T's and F's in the same places. We're going to do one without the truth table with language, okay? So this is the language for the original statement. If I am a sinner, then I am saved by grace. All right, so the first thing I'm going to do is I'm going to underline the individual statements. The individual statements that are in this compound statement are I'm a sinner and I am saved by grace. So one of the things I have to do is I have to switch the order. So the part about grace has to come at the beginning and the part about the sinner has to go at the end. What else do I have to do? I have to negate them. So instead of it saying I am saved by grace at the beginning, what will it say? If I am not saved by grace, what happens next? Put the word then, and then I negate the other piece, and you guys are already telling me that, which is what? Then I am not a sinner. And that is logically equivalent. That's like saying, if I were perfect, I would not need grace. You and I both know that we can't be perfect. But that's the logical equivalent way to write that using the contrapositive.